Hello, honors physics students. Let's take a look at number 6 again, where we left off with in class. We had done number 6 with the free body diagram, and we figured out that the net force had to be 0 because it's moving at a constant velocity, but there was still a tension force to the left of 24 newtons, so we realized that there had to be a force to the right also of 24 newtons to make sure the net force was 0. And then we realized it was moving on a rough surface, so of course we realized that this would be a friction force causing this to happen. Let's talk a little more about friction force. And now we're on the notes page about free body diagrams and types of forces. Our symbol for force of friction is capital F with a subscript F. We define it here as the force that results when two objects are compelled to slide past each other. Notice it doesn't actually say they are sliding past each other, just they're compelled to, which means that maybe they are sliding past each other, like in number 6, where the mystery box is sliding on the rough surface. Or perhaps friction is holding an object in place. You're trying to get the object moving, but friction is holding it there, making sure it doesn't move. So you're trying to get it to slide past. In terms of the direction of friction points, it always points to oppose relative motion. Again, if the object's in motion, it opposes that motion, or if you're trying to get the object to move, it opposes that. Being a force, of course, friction is a vector quantity, so we put the vector arrow above it, and of course the units are newtons, just like for any force. So now we're going to try a bunch of problems, numbers 10, 11, 12, and 13. So why don't you pause the video, try all of number 10 on your own, and then come back to see how I solve it. We're starting with the free body diagram, but of course we know our routine. Before we do anything like that, we always put some information off to the side, and it says it's being pushed to the right, so we know that it's going to be moving to the right, and that's the initial direction of motion, so just like always, we call that the positive direction. It's on a smooth level surface. That's pretty much telling you that there's no friction in this problem. That means that if it's being pushed to the right, it's going to accelerate to the right. There's nothing holding it back. And that also means the net force points to the right. Remember, the direction of the acceleration is always the same as the direction of the net force. Now, why are we putting these vectors off to the side? They're all important bits of information. Well, remember, neither velocity, acceleration, nor net force is a force. Velocity and acceleration aren't measured in newtons, so they're definitely not forces. And even though sigma F is measured in newtons, remember, it is not a single force. It is the combination of forces. And so sigma F never appears on the free body diagram. Now, drawing the actual free body diagram, you know our routine. We always start with the same way, with the force of gravity, also known as weight, and it always points straight down. Remember, we always label what kind of force it is, and then if we happen to know the magnitude, we can put that as well. But we don't just put the magnitude, we always put the type of force, and it's very easy to calculate the weight of this 4-kilogram object. It's going to be 39.2 newtons, and you never ever have to show work to calculate an object's weight. It's on a surface, so of course there's going to be a normal force, which remember is always perpendicular to the surface. And since there's no other vertical forces occurring here, the normal force is just going to support the weight, so we know it's also going to be 39.2 newtons. There's no vertical acceleration. Horizontally, it says it's pushed to the right by 2.40 Newton force. Now, we don't know what kind of force that is, so we're just going to call that the generic force F. If instead you would call that tension, well, that's not really right. It doesn't say anything about a string, so make sure you do change that. It's just, we don't know where this force is coming from. Now, sometimes the book or other sources might call this FAPP for applied force. I actually strongly encourage you not to use that symbol. I find that some students think that FAPP is some new kind of force, when in reality, it's sort of a catch-all, just saying that a force is applied, but we don't know what kind of force it is. And so just to make sure we're not confused about that, we're just going to call that capital F. We don't know how this force is applied, we don't know where it's coming from, but a force is applied. So there's our entire free body diagram. On to letter B, you want to find magnitude and direction of the object's acceleration. So of course we write sigma F equals ma, we always do. Remember, the next step is always to construct sigma F out of our free body diagram. We see weight and normal force cancel each other in the vertical dimension. The only thing left over is the 2.4 Newton force. So in this case, it's positive F equals ma. But remember, we will never start by writing that. We'll always start by writing sigma F equals ma, even if there's only one force causing the net force. I don't want us to do anything different. Let's always follow the routine. At this point, you can just rearrange to solve the acceleration, and shouldn't be any difficulties here. Obviously, you have the answer there. We know it's going to be positive 0.600 meters per second squared. Here, I'm using the sign as direction. You can use words, that's fine as well. I do note there is a typo on the page there. I did leave off the direction. I do apologize for that. So make sure, of course, you have the direction. All right, for letter C, you want to find how fast it's moving after 5 seconds. So I think the best way to do that is VF equals V0 plus AT. It says it starts from rest, so V0 equals 0. And it's not very difficult math here to figure out it's moving at 3.00 meters per second. And let's see how far does it move? Well, you can pick your favorite kinematics equation. I think you know which one mine is, right? Delta x equals v bar t, but remember it's always v bar. It starts from rest, it ends at 3 meters per second. So of course the average speed is going to be 1.5 meters per second, giving a displacement there, a magnitude of displacement of 7.50 meters. Now of course you can do delta x equals v naught t plus half at squared. You can do delta x equals vf squared minus v naught squared over 2a. Any of those is fine. You should be getting 7.5 meters no matter how you do it. All right, so at this point, I want you to pause the video, and I want you to go through numbers 11, 12, and 13 all on your own. Even if you get a little bit stuck, maybe try going on to the next one. Really try to do as much on your own as possible. Only unpause the video and watch my solutions when you get stuck, or if you've gone through all of them and you want to check your own work. All right, on to number 11. Again, we start with the free body diagram. This time, a lot of it is quite similar, except now there is a frictional force, right? And we really want to consider that number 11 does follow from number 10. In fact, when you see there in part C, it tells you it follows directly from number 10. So think of it like a sequence. Problem 11 follows after number 10. And so it's still moving to the right, which we call the positive direction. It's accelerating to the right, the net force to the right. And we know this happens because we can see the force to the right is beating the force to the left. Here's our free body diagram for number 10. It's all going to be pretty much the same thing. The only change is now it's on a rough surface, which means that there's going to be a friction force. Remember, friction always opposes motion. If it's moving to the right, the friction is going to point to the left. And you'll notice, of course, that I drew the frictional force vector smaller than the applied force vector, because it is, right? 1 should be smaller than 2.4. This is rather important in helping you visualize what's happening. It's a very visual reminder the force to the right is winning over the force to the left, and so that means the net force and the acceleration will point to the right. To find the acceleration, of course, it's just going to be sigma f equals ma, but remember, our next step is to list each of the forces with their proper sign. We're calling right positive, so the 2.4 newtons, the applied force is going to be positive, since it's pointing to the right. The friction force points to the left, and to the right is positive, so that's going to be a negative force of friction equals ma. Remember, this is always our step. Then you can go ahead and rearrange and put your numbers in and solve for the acceleration. You just have no problem getting positive 0.350 meters per second squared, or 3.50 meters per second squared to the right. Letter C, you want to find its speed, so just Vf equals V naught plus AT is a good way. Remember, V naught is not 0, because this problem follows from number 10. So the final speed in number 10 becomes the initial speed in number 11. Does that make sense, right? If in problem 10 it left off at 3 meters per second, then in problem 11 it starts at 3 meters per second. So you should be getting a final speed here of 4.75 meters per second. Remember, this is like a sequence of events. Problem 10 happens, then problem 11 happens. By that same logic, problem 12 happens right after problem 11. So here's our free body diagram. It says it's being moved to the right, so we know that's happening. But oh, it says constant velocity. I hope that you noticed that. I didn't underline it, but hopefully you did. Anytime you see constant velocity, you underline it, highlight it, circle it, because it's giving you information. This lets us know the acceleration is 0. Done. Which means the net force is 0. Done. You never even have to think about it. You want to do that right away. So what does our free body diagram look like? Well, it's going to look very similar to number 11, but of course, the net force has to be 0. The only way for that to happen is for a force to the left to be 2.4 newtons to counterbalance the force to the right at 2.4 newtons. And of course, that's going to be a friction force. In fact, it even says it's a rougher surface. Remember, friction kind of comes from the roughness of a surface. And so this time, the friction force just counterbalances the force to the right. And so now the object is maintaining its motion, just not speeding up or slowing down. So what's the acceleration? Well, we're already done, right? Once you read it in the problem, you don't have to do anything with that. You're done. What's the block's speed after being pushed another 5 seconds? Well, I mean, you could do the math, but really just think about this, right? If the acceleration is 0, it's not speeding up or slowing down for problem 11. We know what's going to happen. It's still going to be moving at 4.75 meters per second, because that's the speed it left off with in number 11. Now, if you really need to prove it, of course, you could do the equation, Vf equals V naught plus AT. The initial speed, of course, is the final speed it had back in problem 11, the 4.75 meters per second, but the acceleration is 0, which means it's still going to be moving at 4.75 meters per second. So at this point, if we're starting to realize you're getting some things wrong in numbers 11 or 12, maybe you do want to pause the video and try number 13 again. Make sure, of course, you fix things you did incorrectly in numbers 11 and 12, but maybe you're doing something wrong a couple times, and now you want to make sure you're doing correctly for number 13. Again, this is a sequence of events. So number 13 follows directly after number 12. So here's our free body diagram. It's still moving to the right, right? If it was moving to the right in problem 12, it's still moving to the right in problem 13. Just because you let go doesn't mean it instantaneously stops moving. In fact, nothing can instantaneously stop moving. So it's still moving to the right. Remember, an object in motion stays in motion for some amount of time. Maybe it's going to stop shortly, and we'll figure this out, but it's still moving. Now, which way is it accelerating, which way is the net force? Well, maybe we should draw the free body diagram first, okay? So we're going to start with our usual stuff. We have weight down, normal force up. Of course, nothing's happening vertically. And it's still on the rougher surface, which means the friction force is still there, right? And friction opposes motion. So it's moving to the right, the friction is to the left. I just realized there's a little bit of an error here. Please make sure that your length of this friction vector matches the same as number 12. Okay, so look at our free body diagram. Vertically, the forces cancel, but horizontally, we still have the friction force to the left. So it means the net force has to point to the left. And of course, we know the direction of the net force is the same as the direction of the acceleration, which means the acceleration is to the left. So now at this point, you're beginning to look confused and saying, well, how could this happen? If it's moving to the right, how could it be accelerating to the left? Well, we've covered this before. Back when we did it in linear motion, we had a big idea about this, right? Anytime velocity and acceleration are pointing in opposite directions, what's happening? That means the object is losing speed. The object should be slowing down, which makes sense. If you're pushing the object along a rough surface and you let go, all that's left over is friction. What's going to happen? It's going to slow down. Friction is going to cause it to lose its speed. So this is making sense. All right, we want to find the magnitude and direction of the object's acceleration. So of course we do sigma F equals ma. Looking at our free body diagram, weight and normal force vertically cancel. The only thing left over is the force of friction, but it's pointing to the left, and we're calling right positive. So in this case, it's a negative force of friction equals ma. It's always so important that we look at our free body diagram, look at the direction of the vectors, and then compare it to our positive direction. The friction's pointing to the left, we're calling to the right positive. That's a negative force of friction. So now when you go ahead and solve for the acceleration, we should be getting negative 0.600 meters per second squared, or 0.6 meters per second squared to the left. How much time is it going to take for it to stop? Well, these are kinematics equations. Personally, I would think this is the easiest one to do. T equals Vf minus V naught over A, just the acceleration equation rearranged. We know it's got to stop, so the final velocity is going to be 0. It's really, really important that we have the negative sign on our acceleration, otherwise you might end up with a negative time if you're not careful with the algebra. And of course, negative time wouldn't make any sense. And so here we're going to get 7.92 seconds. That makes sense, right? It's going to take some amount of time for this object to lose its speed because friction is slowing it down. Now, before we move away from this, let's look at number 12 again. Number 12 is kind of interesting when you look at the free body diagram. We have normal force and weight equal and opposite to each other, with the force of friction and the force applied equal and opposite to each other. It looks like, just by looking at the free body diagram, this object shouldn't be moving, and yet we know it's moving because in problem 11 it was moving. This is quite similar to what we had done back in problem number 6. We had a very similar looking free body diagram, right? The weight and normal force vertically are canceling, the horizontal forces are canceling, the net force is 0, acceleration is 0, but the object is in motion. So what we learned from this is when we look at the free body diagram, it doesn't really tell us about what the object is doing right now. The forces are canceling, so the net force is 0, so the acceleration is 0. But remember, acceleration is not motion. Again, this is one of our big ideas back from linear motion. Velocity is motion. Acceleration is how quickly motion changes. And so if the acceleration is 0, that's not saying it's not moving, it's saying nothing's changing about its motion. How do we know it's moving? Well, because we follow the sequence of events. In number 6, this followed from number 5. In number 5, it was moving, so in number 6, it's still moving. In number 12, we know it's moving because in number 11 it was moving, and number 11 leads directly into number 12. So it was moving in number 11, it's still moving in number 12. The free body diagram doesn't tell us that, though. We have to know more information.